In this video, we're going to take a look at a problem I've created called the Cannonball Bonanza. And the aim of this problem is to help you see how powerful thinking about physics is when you look at it only using variables. In other words, we won't be plugging in numbers into specific physics equations to solve for results. Instead, we'll just be doing it all symbolically and coming down to some expressions that will give deeper meaning into the phenomenon that we're looking at. Now, in order to get those relationships, i.e. the equations that govern how nature works, we actually have to do experiments in the lab in order to discover those relationships. But once we find them, we can then apply them and extract out of them all sorts of wonderful insights that help us predict how the world works. For example, say you had a ramp and you could allow a car to roll down the ramp from rest. So up here, and eventually it would speed up, of course, and be going at some speed v at the bottom. Notice I'm not even specifying an exact number of meters per second for our speed. I'm just calling it a variable v. And then over here, if we were to change the angle to something much larger, then we would expect the car to be traveling much faster down here at the bottom of the ramp. But we would want to know precisely how much faster. What is the exact relationship that exists between the angle of a ramp and how fast a car will be going at the bottom of the ramp, given that it starts from rest at the top, assuming also that it travels the same amount of distance in each case. So the length that the car travels here is exactly the same as the length the car travels there. Now, that type of question could be answered by taking some numbers and plugging them into some equations and getting the exact number of meters per second, or it can be done by just looking at the relationship between those two variables after you have derived an equation from some basic physics principles. And what you will notice is once you've derived the equation and you have it and it's in variables, you really should be able to tell what nature will do from that equation. Now, this problem, we're not going to be doing that for a car rolling down the ramp. Instead, what we're going to be doing it for is a cannonball that is shot straight up from the ground, and we're going to be analyzing the properties of that what's called free fall motion a little bit more abstractly than we would if we just plugged in numbers in a typical type of problem. So let's get started with that and see what insights we can make by really focusing in on the relationships that exist between the physical variables that we'll see. Now, before we get into this specific question, it's important to review the nature of freely falling objects that are dropped from rest. And if we drop an object from some height above the ground and we ask the question, where will it be located as time goes by before it hits the ground, we can figure that out. We have an equation that'll help us do that. It's called the second equation of motion here, and I've written it out. And there's one constraint here, and that is that we're going to drop the object from rest. So the initial velocity in the vertical direction here will be equal to 0 meters per second. So we can actually come up at the top and cross this term out because it'll be equal to 0. Likewise, if we start our ball at a position of 0 meters, which we're free to do by just coming right in here and saying, let's let that equal location of 0 meters. You're always free to choose your 0 point wherever you'd like to in a coordinate frame. You just got to keep it consistent throughout, working through a question. Then we can cross that out as well. So that simplifies our equation down to this wonderful statement that basically says that the ball will be located at the position that is equal to 1/2 multiplied by the value of the acceleration multiplied by the square of the amount of time that has elapsed. And that is really where the heart of this relation is. And we'll write that in a way that doesn't use an equal sign, but instead uses the proportional reasoning concept. So we can see that here, where I've taken the variables y, which is position, vertical position, and t, or clock reading or time, and I've put that up here, and we're going to assume our acceleration is constant, which it is for objects freely falling close to the surface of the Earth. And we can then now write and say that the vertical position of a ball dropped from rest, got to remember that we did not give this any initial velocity at all. That vertical position of that ball is proportional to the square of the amount of time that has elapsed. And that is really where the knowledge exists in this formula. And what's cool about that is some really cool insights about nature now emerge. And by looking at this relationship, we can really start to see what happens when an object falls and understand and be able to predict what will happen next. So let's get into this relationship and really see how it works. And to do that, we're going to do it in two ways. First, we'll just plug in some numbers so you can see how the pattern is building up, which is pretty obvious. But then we'll learn to do this in a slightly more abstract way, but a much more powerful and quicker way to analyze this relationship. And that'll pay off later when we have many other relationships in physics where we want to be able to just understand them quickly without having to actually plug in numbers. So to do that, let's just go through the numbers right now. And I've created a little data table over here, and we'll just plug in some time values and see what the corresponding positions are. And I've also set up a coordinate system for us such that if the ball is going down, which it is the whole time in this example, we're going to call that the positive direction. So that would mean that these vertical values are always going to be positive. Now, because of that, the acceleration from gravity, or better called the gravitational field strength, that value is going to be a positive number. And we're going to use positive 10 meters per second for every 1 second, or 10 meters per second squared in this example, just because I like to round that for simplicity. So I'll write that over here, that the field strength is 10 meters per second squared, which again is 10 meters per second for every 1 second. That's a better way to say those units when you're first learning it. And that is our acceleration, and it's a positive value here because we've chosen down to be positive in this problem. So pause the video and go through and see if you can just get this data table correctly in terms of the numbers, and also look at your numbers and see if you can see some type of pattern. I think you'll be able to find something pretty interesting here if you plug it in and then you look at it. All right, so pause it and we'll come back. So I've worked out the numbers, and you can see over here on the left the data table showing exactly where the object's located at particular moments in time. Over on the right, I've done a sample calculation for a clock reading of 2 seconds, and we find that the object is located at a vertical position of 20 meters below where it was dropped from. One thing to note is that the seconds, or this, I should say the units, cancel out perfectly here. The seconds squared cancel out with these seconds squared, and we're left with meters. You always want to do a check on the units when you're first learning an equation, and it's good practice anyways, so you make sure that you're getting things that make physical sense. Now, let's go ahead and write these numbers down in terms of the vertical positions next to the little dots I've put up here. So up here we're at 0 meters to begin, and then we've traversed down to a position of 5 meters. Then we're at 20 meters, a little bit later in time, or exactly at 2 seconds. At 3 seconds, we find that we're located at 45 meters, and then right at the 4th second, when the clock reads 4, we are at 80 meters. So it's pretty clear that as time goes by, we are increasing the amount of our position, and we're also traveling further and further distances. So if you look here during the 1st second, right in this area here, we've only traveled 5 meters. During the 2nd second, though, we've traveled a lot further. In fact, if you calculate that, you can see, well, if we're at 5 here, 5 meters, and then we're at 20 meters here, it's pretty clear that we've traveled 15 full meters during that 2nd second. And then likewise, during the 3rd second down here, we've traveled even further, 25 meters, and then further still as we go down. We'll get to that pattern about the distances in a little bit. Let's go back to the position, so where the ball is located in space, and see if we can find a pattern there. So if we look at this, as we allow the ball to travel for 1 full second, it ends up at a position of 5 meters. Then if we allow the ball to travel for 2 full seconds, we see it ends up a lot further, 20 meters. Is there a pattern we can see here? Well, you've probably noticed it, and I'll help us kind of see that by writing this out. If we allow the ball to go from, instead of traveling 1 second to now being allowed to travel for 2 full seconds, we'll see that we've doubled the amount of time we allow it to travel for. And what is the effect then on the vertical position? Well, 5 going to 20 is a quadrupling of its vertical position. So that's interesting. When we double the amount of time that we're allowing this object to fall for, apparently the position is changing by a factor of 4, or it's quadrupling. Now, that's just one scenario or one case. Let's see if that pattern gets upheld in some other places in our little data table here. So can you find another doubling in time? You should be able to. In fact, if we go from 2 to 4 seconds, there's another doubling. So we'll write in, it gets a little messy, but we'll put in times 2, meaning we're multiplying the amount of time times 2, from 2 to 4. All right, well, let's pick out the subsequent position data here. So we would go from a position of 20 all the way to a position of 80. Well, if you look at that, that's also a quadrupling. 20 times 4 is 80. So apparently, when we double the amount of time that we allow this thing to fall for, it looks like the position is quadrupling. I wonder if that will be upheld in another place in our data table. Let's do it one more time. So from 3 to 6 seconds, that is also a doubling of time. And we can now see, this gets a little messy, but we'll go here from a position of 45 all the way down to 180. And indeed, if you multiply 45 times 4, you will get 180. So far, it looks like doubling the amount of time will quadruple the vertical position. Now over here in green, I've written out a useful way to show that. So the effect of doubling the time would be to multiply some value of time, and it's more generic if we just leave it as t as a variable. So pick any amount of time, it doesn't matter. If you double that amount of time to 2 times as much, then we'll see that the position that had happened before the doubling, which we just call y, has then changed to 4 times the amount. What's nice about writing it like this is it's not relying upon any specific numbers over here. It's a little bit more general. And you should be able to realize that, we picked out different amounts of time. We started from going from 0 to 1 second and then from 0 to 2 seconds, meaning a doubling in time. And then we picked out 2 to 4 and then 3 to 6. So we were changing this amount of time, and it's very useful to make that more compact by writing it like this. Now, are there other types of these relationships? Why don't you pause the video and see if you can find out what happens when you triple the amount of time that you allow this object to fall for. What will happen to the vertical position then? Try it and see what you find. So when you did this, you should have seen that if you triple the amount of time you allow this thing to fall for, the position would change by 9 times as much, or a factor of 9. And that's clear from the numbers here. If we allow it to fall for 1 second, it will reach a position of 5 meters. But if we allow it to fall for 3 times as long, or 3 seconds, you can see that now we would be at a position of 45 meters. And that's 9 times as far as 5 meters, because 5 times 9, of course, is 45. So we can consolidate this as a statement as well over on the right, and we can see that if we now triple time, our vertical position changes by a factor of 9. Now go ahead and try it one more time, but this time, what happens when we quadruple, or 4 times the amount of time we allow the ball to fall for? And if you can look at the result and you get this right, you should be able to see a very interesting pattern start to emerge. You might already see it, and I'll help you a little bit by underlining 2 numbers here. The first one is 4, and then the next one is 9. I wonder what number we'll get next in this little example, and if you get it right, I think you'll see this right away. So pause the video again and try that. So I've worked it out here for 4 times as much time, and you can see that the effect is to change the position by a factor of 16. So allowing the ball to fall for 1 second, we'd be located at 5 meters over here, but then allowing the ball to fall instead for 4 times as much time, or 4 full seconds. Now we're at a position of 80 meters, which is 16 times as far from when we only allowed it to travel 1 second. So this wonderful pattern now starts to emerge. When we double the time, we quadruple the position. When we triple the amount of time, now our position will change by a factor of 9. And then when we quadruple the amount of time that we allow the object to fall for, our position will change by a factor of 16. Now, if you look at this pattern, 4, 9, 16, and then you also look at the fact that we're doubling, tripling, and quadrupling, you should see something pretty cool. And what you're seeing is the square relationship, and it's right over here. And I'll put a box around this. This is called the square relationship. And you can see why it's called that, because we're squaring one of the quantities over here, and that has an effect on the other quantity, namely the vertical position. So to finally see this, if we square the factor by which we have changed the time by, so in the beginning we're changing it by a factor of 2, or a doubling, then if we square that factor, look what we get. We get 4. When we square the factor, sorry, not square, when we triple the factor that we're changing the time by, look what we get. We get 9. And when we quadruple the factor that we're changing time by, and if we square that factor, we get 16. So what's really nice about writing out physics in terms of the relationships is that we can very quickly see what the effect of changing one parameter will have on another. And that's what I had up here in this box. Physics is all about the relationship between variables. And so we can see here that very quickly, knowing how we change time, comparing two experiments, we can easily see what will happen to our vertical position. You could extend this further. You could say, okay, well, if we allow the ball to fall for 10 times as much time, so 10 seconds instead of just 1 second, we would see that it would travel 100 times further. So it would be located not at 5 meters, but 500 meters. And that's pretty remarkable that all that information can be consolidated in such a simple little statement here. Now, let's find another pattern in this wonderful falling ball experiment, and it has to do with the distances that the ball travels in equal time intervals. So here's a simple question. How much distance did the ball travel in the first second? Well, we already have it kind of worked out. You can see right over here, we started at a position of 0 meters, and after 1 second has elapsed, now we're located at a position of 5 meters. And the ball just went straight down continuously, so we traveled a distance of 5 meters. We'll go ahead and write that out here. And I'm going to use a different color, and I'll put it over here on the side on the left. Realize that what's over here on the left is not the position now, though, but it's the distance traveled by the object just in the amount of time in between the two dots shown here. So during the first second, we travel 5 meters. In fact, just to make it even clearer, I'll say during the 1 second here. Okay, now, during the next second, which is in between the clock reading of 1 and the clock reading of 2, how far do we travel? Well, we started at a position of 5 during that second. We ended at a position of 20, so we must have traveled 15 full meters during that second. So we'll write that in here, that we have now traversed 15 meters. However, an important note to note is that we only traveled for 1 second during that, in between those two dots. So the same amount of time has elapsed in between the image of the ball here in these two locations and the image of the ball here in between these two locations, right? But we've traveled a lot further. In fact, can you see how much further we've traveled? Well, we traveled 5 meters in that first second, and over the next second, 15. So that's 3 times as much distance. That's pretty incredible. Now let's keep doing this little pattern, and you should be able to see that, all right, well, during this next segment, we've gone from 20 meters to 45, and so we've traveled 25 full meters during that second. And then during the next second down here, well, we started at 45 meters, and we ended up at a position of 80 meters, and that, if you just do the math, would give you 35 meters. All right, so pause the video now, and I want you to take a look at these distances. Can you find a pattern that is occurring here? We have 5 meters, then 15, then 25, then 35. I wonder what's going on. Pause it and see if you can figure it out. So to see the pattern, let's really focus in on that first second. In that first second, we have traveled 5 meters. I want you to keep that number 5 meters in your mind. During the next second, we've traveled a distance of 15 full meters. How much bigger is that as a factor than the 5 meters? Well, it's 3 times as much. Now, during that next second, we travel a distance of 25 meters. How much bigger is that than the first second? Well, it's 5 times as much. 5 times 5 is 25. And during the next second, down here, the fourth second, we have traveled a distance of 35 meters in between this dot here and the dot down below. That's 35 meters right there. And how much bigger is that than the first amount of distance we traveled, which was 5 meters? Well, it's 7 times as much distance. I think you could probably realize, and if you look back at the data table, you could prove it, that the next number in this little pattern will be 9. And so what you're seeing is the very famous odd integer pattern, which basically just goes 1, 3, 5, 7, 9, 11, dot, 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 and it'll just keep going, where the amount of distance that we're traveling in equal time intervals is following the odd integers. And this was a massive discovery made by Galileo, and it has historical significance because it overthrew thinking from people long before who thought it followed the even integers in terms of this pattern. This was a massive discovery, and it was all done through experimentation and focusing in on that fundamental relationship that we looked at. Now, I'd like to connect these little distances during equal time intervals to the positions that the ball is located that we saw before. And if you look at this clearly, you can see that right down here, we would have traveled 4 units of distance straight down. And so our position is showing that familiar pattern where we're getting 4 down here, and then we're going to get 9, and then 16 units of distance. And these numbers are all in reference to that first amount of distance that we traversed during the first time interval. You always want to keep that in mind here. So during that first time interval, we're just calling that 1 unit of distance, whatever it is. And then the next time interval, 3 units of distance, and then 5, and then 7. And we can see if we add that 1 unit of distance to 3 units of distance, we get 4 units of distance. And then add on 5 more units here, and we get to 9 units of distance. And then add on 7, and we get to 16. Now, that will work for any particular number of meters that this travels for. We're not talking about 4 meters, 9 meters, 16 meters. We're just saying a more abstract idea where we're calling this whatever unit of distance that nature provides for us. Here on the Earth, we could exactly calculate it when we drop something, and we would get the numbers that we precisely determined before. But if you go to other places in the universe, you'll find that the field strength of gravity, that 10 meters per second squared, changes to different values. And so these won't be the same numbers that we got. However, the pattern of 1, 3, 5, 7, and 4, 9, and 16, this type of pattern will still hold, just with new numerical numbers of meters. So it's an interesting thought to think about. One more final little cool nugget of knowledge here that you should take away from the falling ball is to compare the little distances that are traveled as time goes by. So for example, in our first amount of time, we traverse 1 unit of distance. And then in that next equal time interval that occurs right here, we triple the amount of distance that we just traveled. That's pretty remarkable. Imagine doing that, traveling along a road, down a street, and then all of a sudden, during the same amount of time that it took you to travel down that road, now traveling 3 times as far, right? You'd really have to be moving faster to do that. Now, what happens during the next equal time interval? Do we travel 3 times as far as we just did? Well, if you look here, no, we don't. You can see that we travel 3 units of distance, and now we only travel 5 units of distance. If we continued this pattern of traveling 3 times as far like we did here during the second time interval compared to the first, we would expect to have traversed 9 times or 9 units of distance right here. But we didn't. We only traveled 5 units of distance. So in terms of a number, of a factor that we've now multiplied by, if you just take 5 and you divide that by 3, I'll write that out over here, that'll give you the ratio now of how much further we traveled during that next time interval. And that'd be about 1.67. And I'll actually do the first one as well over here. So 3 divided by 1, of course, is 3. So we traverse 3 times as much distance as the preceding time interval, but now we only traverse about 1.67 times as much distance as the preceding time interval. And you can do that again by dividing 7 over 5, and then 9 over 7, and then 11 over 9, and then 13 over 11, dot, dot, dot. And you'll see that as time goes by, these numbers are going to get closer and closer together, which means ultimately the ratio will approach 1, which means really far out in time, if you keep accelerating like this, the amount of distance that you'll travel in the next time interval will be very, very close to the amount of distance that you just traveled. So in the beginning of the motion, that acceleration is having a huge effect in terms of a proportion on how far you're traveling. But later in time, it's not having as much of an effect as in terms of the distance that you're traveling in that next time interval. Now keep in mind the position that you're reaching is definitely increasing dramatically with that square relation that we looked at last time, but the additional distance that you traverse in those in that next amount of time kind of levels off as time goes by, or doesn't level off, but it approaches 1 essentially. You are always traveling slightly larger and larger distances, but it's an interesting thought to see that it's not tripling like we saw in the beginning of the motion. Pretty cool. You might also think about, why is that happening? What's the nature of our motion really far out in time? I'll give you a little bit of a hint here for a thought experiment you can do on your own time, that further out in time that we allow this thing to accelerate for, we're traveling really, 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 really fast, faster and faster. So think about that, and you might be able to logically figure out why this kind of like law of diminishing returns is occurring here in the distances we're traveling. So now we're finally ready to get to this Cannonball Bonanza problem. And this problem is a little bit more challenging than a problem where you're just plugging in numbers to the equations of motion in the context of free fall, where objects are going up and down in one dimension here, because it's going to require you to just use symbols or variables in your analysis. And that is challenging in the beginning because it requires a higher level of abstract reasoning, which when you're in an introductory physics course, you're building up those skills and you're looking at them in a new way that you're probably not used to in, say, a math course or something like that, depending on what kind of math courses you've taken in the past. And you're also combining that with the physical world in a totally new context. So it can be very challenging. So what we want to be able to do in this problem is just to kind of slow it down and to really think about, what are these symbols and variables that we're writing down? What do they mean? And how can we manipulate the equations and solve for things and then use that information more symbolically? So let's get into that and see how it works. Now, one of the first things you always want to do in a physics problem is set up a coordinate system. What direction is positive and what direction is negative? I can't stress this enough, because if you get a positive or negative sign error in a certain part of your problem, that can trickle down through the rest of the problem and really give nonsensical results in terms of the algebra that you're doing. You might get the square root of a negative number or these other things you just can't do mathematically, and it will just really be confusing. So let's pay special attention to those positive and negative signs as we work through this. And in this problem, we'll choose up to be positive this time and down to be negative. And there's a little price to pay for that, and you'll see that in just a second when we get to writing out the quantity g, the gravitational field strength. But first, let's just read. So we see that a cannonball is shot up at a speed v. Notice I've used the word speed, and that quantity is inherently a positive number. So if you were to plug in a number for v, like plug in a speed of like 30 meters per second or something, then it would be a positive number. So just let's keep that in the back of our minds as we look through this. And then the question is, how high will it go before coming back down? And also, how much time will it take to reach this height? So another skill is converting the language into symbols and variables. Let's do that. So how high will it go before coming back down? Well, it starts then from an initial vertical position. I'm calling that y subscript I, which stands for initial, down here at the ground. And then it will reach up here a final position, and I'm calling that y final, or the final vertical position. Now, something very special when it gets to that final spot up there, the highest it will go, well, it won't be moving at all. So it will have a speed of 0 up here. And then finally down below, I've written out that it is being launched up at a speed v. All right, so how high will it go? Well, I've written in that the final velocity will be 0 meters per second at that top spot. And Now let's look at our equations of motion, and if you look at them to yourself for a second, you might be able to pick out the correct one that we need to use, and it's going to be the third equation of motion that I like to call the third equation. And it looks like this. The final velocity in the vertical direction squared is equal to the initial velocity in the vertical direction squared plus 2 times the acceleration multiplied by the displacement or change in the vertical position. So how can we use that now? And remember, we're not plugging in any numbers. So let's see how to use this and pay very careful attention to the sign of the quantities that we're putting in. So right here at the bottom, we can see that, look, if we throw this ball up at some speed v, then its velocity will be positive because we're moving up in the positive direction. So whatever we have here, it's going to need to be positive. Well, let's plug in for the variable that we're going to use here, and that's v. So I'll come in and put that right up here, but we need to square that. Right? Now notice, it's when we plug in for v, if there was an actual number, which there's not, but if there was, this would be a positive number. And so it makes sense that we don't need to put a negative sign out in front of v in this case. Now, we'll see the opposite, though, happening over here with gravity, with the field strength. So our acceleration will be a negative number in this case. And to write that number here, I'll write it down here. As a number, it would be negative, and we'll just use 10 meters per second squared. That's the actual number with the right sign. Now, what we do in physics all the time is instead, we like to write the gravitational field strength as just a positive number always in an equation. So whenever you see g in an equation, you're going to think that that is just positive 10 meters per second. Now, the price you have to pay for doing that is you, as the physicist, have to come in and put a negative sign intentionally in front of that variable if you just leave it in an equation. I'll show you what I mean here. So if I come over and I now say that, okay, well, we're going to accelerate at g here, and then we need to put in our delta y, which we'll get to in just a little bit. Well, this is now basically an incorrect statement, because if you look at it, think about it. If somebody came in and plugged a number in now to actually solve for the final velocity, well, we all agree that this should just be a positive 10, because that's what that means whenever you see g in an equation, positive 10 or positive 9.81 meters per second squared. But we've eliminated the negative sign, right? There's no negative sign to take into consideration the fact that down is negative here. So we actually have to manually go in and put that in our equation. So to do that, I'll erase this this positive sign here, and we'll come in and put the negative right down in there. I'll do that in red. Okay. Now this makes sense, and it should make sense to you because look, if we were moving at some initial velocity here, upwards, a very positive initial velocity, then what we would expect to happen as we went and were displaced up, we'd expect this term over here to subtract off from that velocity, because clearly we have to slow down as we go from where we were shot up here all the way up to the top. So this is our maximum value of our velocity after, of course, you take the square root. And we would want this term over here to be lessening that as we get closer and closer to the top of this spot up here. Okay, so now we've got that figured out. We manually put that minus sign in. That's looking good. Now what we need to do is take care of this term over here, the delta y. So let's go ahead and expand that out. See what happens. So we get our square of our initial speed there, minus 2g, multiplied by our y final minus our y initial. All right. That's cool. One simplification that we can make usually in problems is we can set our initial position to 0 here. That will really help things out. We can then just cross this out, and that goes to 0. Nice. All right, let me clean this up so I can get this out of the way. I have a little more space to write. And now we can come and continue with this. So we're almost there. And this y final, let's call that something else. Why don't we call that y max? And that's helpful to do because it'll remind us that, hey, that's the maximum height that we got to. All right, and then finally, the last thing to realize that we did before is, well, at that maximum height, at this position that we're plugging in for right here, we can see that our final velocity is 0. So we plug that in, and now everything kind of falls into place in terms of the signs and the quantities, and we'll solve for this. So I'll get my coordinate system out of the way here, and we'll bring this over to the left, and we will see that when you solve for y max, look what we're going to get. It's pretty cool. The maximum height is going to equal the square of that initial speed divided by 2 times the gravitational field strength. Now, that's pretty cool. And what I'd like you to do is think about this for a second and just imagine if we were to double the initial launch speed of this cannonball. So instead of launching it at a speed v, we launched it at a speed of 2v. And if you really thought about what we did in the previous part of this video with proportional reasoning and looking at relationships, you should now see exactly what's going to happen to that maximum height if we were to double that initial launch speed, while of course keeping the field strength of gravity the same value. Pause the video and see if you can get that. So incredibly, we see that the maximum height that a ball will get to if launched at some initial speed v, it follows the square relation. So doubling that initial velocity will quadruple how high it goes. And if we tripled the speed, then we would get this thing to go 9 times as high. That's pretty remarkable that now we can really see what's happening in nature quickly because we've identified a relationship. A little bonus relationship is with the gravitational field strength. So for example, if we had this giant fictitious button where we could perhaps double how strong gravity is, then we would find that it would only go up half as high. And the reason that occurs, of course, is because, well, the relation between the maximum height here and the field strength of gravity is called the inverse relation. So if we were to double the gravity, then the y max would be a half. If we were to triple the gravity, this would only go up to a third as high as it did. Notice we don't have a squared type of a relationship here, so we're not seeing that 4, 9, 16 pattern. It's just the inverse relationship, which operates a little bit differently. So that's cool. This is now a general statement that we can take into any planet anywhere in the universe where we have a constant field strength and we launch something up straight up at any speed v. We now know exactly how high this thing will go as we start to change that speed. And that's really, I want to stress that point. When we're trying to understand physical phenomenon, we're always trying to change one parameter and see how that affects the other parameter. That really gives you that predictive ability to look at the world and say, here's how the world's going to change when I do such and such. And that has tremendous power. Now, what about the time to get to this maximum height? I wonder what that depends upon. Well, if you think about it, if we shot it up faster, then of course it would take a lot longer time to get all the way up to the top. That comes from your direct experience. And if we shot it up slower, it wouldn't take that much time to get up to the top of its path. But really, what is that relationship? And how does it operate? Why don't you pause the video and now see if you can do this on your own after I've shown you this first one with the maximum height. And I'll give you a hint. You don't want to use the third equation of motion here like we did. You want to use what I call the first equation of motion, which has to do with velocity and time. So see if you can identify that equation and work through that. Okay, so I've written out the first equation of motion here, which says that the final velocity of this ball will equal the acceleration times the time plus the initial velocity. And you really need to make sure that you see that these are velocities. The sign matters, positive and negative. Now over here, we're going to write this term in terms of this variable v, which actually represents just speed. So these values would always be positive. Now, lucky for us, on the way up here, we can see that our velocity will be positive, and therefore we can just plug a v in over here. However, likewise, we saw in the previous example that because the variable g, which stands for the field strength, That inherently is a positive 10 meters per second squared when we write it down. We all agree upon that. But in this equation, we would actually need to take into consideration the fact that down is negative, and therefore our acceleration value from gravity should be a negative number. So we have to manually put that negative sign out in front to make this equation work. So let's do that and plug that in. So we get 0 meters per second equals a minus g multiplied by our time plus that initial speed term that we're plugging in over there. And now when we rearrange this, we can clearly see that the result we're going to get is that the time to get to that maximum height, which I'll call t to the top, why don't we call it top, it would be the the speed divided by this field strength. Notice again that we're using these two variables, and our initial speed and the field strength, but these are again both positive numbers, and they represent just magnitudes of how fast we're traveling and then what our acceleration is. So what's the relationship here? We can see that, well, the amount of time it will take for this ball to get up to the top is going to be directly proportional to the initial speed that we launch it up at, and inversely proportional to the field strength of gravity. So that's such an important relation that we'll actually, again, write that out. So I'll erase this stuff over here, and we'll use the proportional symbol to show then that the time to the top is directly proportional to the initial speed we launch it up at, and the time to the top is inversely proportional to the gravitational field strength. That looks very similar actually to the maximum height, except we see that the maximum height is proportional to the square of the initial speed, whereas the time to the top is only proportional, or is only directly proportional to the initial speed. It's an interesting distinction. Okay, so we'll come up here, and I'll actually write time to the top right up here, v over g, and kind of just summarize that information right up at the top there. The next part of this question asks about how fast the object is going, the cannonball is going, when it's halfway up. So imagine we launch it here at some speed v. Well, how fast will it be going when it gets to half as high as it's going to get? Interesting question. Now you might think, hey, it's just, I don't know, v over 2. It's half the initial speed. Turns out that's not going to be the correct result, as we worked out in a numerical problem before on my previous video in freefall. But now we're doing it in variables here, and we're really going to see an interesting solution. I mean, I've actually already kind of given out the answer right here. We're trying to prove that the velocity halfway up is the initial speed divided by the square root of 2. Interesting. And then on the way back down, of course, it's going to fall back down, and we could ask the same question. Now on the way back down, when it's halfway down, show that the speed is, show that the velocity is negative v over the square root of 2. Notice, very importantly, again, this v here is the speed of the object, which is always a positive number. So on the way back down, of course, our velocity must be negative. So that is why we have to put manually a negative sign out in front there, because if this were a numerical problem, people would always be putting in positive numbers for this speed, because speed is always positive. So let's prove this, and in doing so, we'll really show, again, how we're using the abstract reasoning just in variables to figure this out. Now, an important note here is that I've left this information from before, from the previous part of the problem on purpose, because that's new knowledge we've generated that we can now use throughout the rest of the problem. And there's way too much information most of the time in a physics problem to try to keep in your head to think clearly. You won't be able to. You need to write it down, get it out of your mind so you can visually refer back to it and say, oh yeah, that's what that was. Now I can use that in this part of the problem. And you want to keep that as organized as possible. The more disorganized and diagonally slanted it is on the half ripped off paper that you're using, the less likely you're going to solve this problem successfully. So keep it organized. Now this question's asking, how fast are we going to be going and in what direction, right, the velocity, when we're halfway up? Well, obviously it's going to be a positive velocity, but how fast are we going to be going? Well, the answer, of course, was the initial speed divided by the square root of 2. We've been given that information. We want to try to prove it. How? Well, what is halfway up? interestingly, we have all the way up. It's called the maximum height. So what would half of that be? Well, this value divided by 2. So it's pretty actually logical if you think about it. All we have to do is come over here and take y max and divide it by 2. Well, what would that be? Well, clearly you can see that would just be v squared divided by 4g, as that 2 comes down and multiplies by that other 2. So this position here, then, halfway up, we'll write this as a position y of v squared, our initial speed squared, divided by 4g. So this will now be the position we're located at the moment we are halfway up. Now we want to know how fast we're going at that particular moment. So what we can now do, and this is a very important skill, is we can deliberately change our final velocity point. In the first part of the problem, the final point we were concerned with was up here when it got to its maximum height. However, it doesn't always have to be at the maximum height. The final point could be anywhere you want to get new information in a problem. And so now we want to have our final position be here, halfway up. So let's see how that kind of cascades through this third equation that I've written down over here, which we're going to need to solve this. And likewise, our initial point is still actually right here, right when we've shot the object at a speed of v or a velocity of positive v there. So let's plug that in and see what actually happens when we do that. So over here, we'll have v squared, that's our initial velocity squared, plus 2 times the acceleration times our displacement. However, remember, we need to actually change this to a minus sign out in front, and that came from the fact that down is negative and our field strength g is inherently a positive number when we write it as the variable g, so we need to manually put that minus sign out in front. And then we can expand our displacement to be, again, a final position minus an initial position. And we'll remember, of course, that this is 0, our initial position. We've set that arbitrarily equal to 0. And now our final position, again, it is not the maximum height anymore. We've deliberately changed it to be this new position halfway up. And when we plug this in, we'll now get our velocity at that point right there, not up here at the top, but halfway up. So let's plug it in and see what happens. In fact, I'll pause and let's see if you can actually plug in the right stuff and get to the correct result. Pause the video and work it out. All right, so I've done some of the algebra here, and I've plugged in for my halfway height, I guess, if you will, which is y equals v squared over 4g. So that is our expression for halfway up for our final position. I've plugged that in here. And what's really remarkable about this is that we're writing a position in terms of some other parameters, velocity here, or speed, I should say, and the field strength. And now we can plug that in, and if you look, some great things cancel out. The g's, or the field strengths here, on the top and the bottom cancel out, remarkably. And then the 2 over the 4 would just be a 1/2 on the bottom, and then we're left with the v squared. And now we just get v squared minus v squared over 2. So that's something minus half of something, which just gives you half of that something. And that's going to equal our final velocity squared. So we would need to take the square root. So let's work that out and show that. So we would then get that the final velocity, and we're going to, let's call this actually the velocity halfway up. It's always helpful to put subscripts on things. That's kind of a longer subscript, but that would be equal to the square root of v squared over 2. And now if you just take the square root of the top and bottom of that expression, you'll get our final result, which we'll write over here now. So we get that the velocity halfway up is going to equal, well, when you take the square root of v squared, you're just going to get v, and then there is our root 2 on the bottom. So there we have it. We've proved it. And look, we also get a positive number. Now, inherently, when you take the square root of a number in math class, you do get a positive and a negative value. So you have to intuitively know in this case that, of course, the velocity would be positive because we're moving up in this case, because we have not even gotten to our maximum height yet. Now, what about halfway down? How are we going to figure that out? Well, again, we got to remember that we're always free to change our initial and final moments. And in this case, we do need to do that. And now what we'll do is we'll say, all right, the ball's traveled up, it's at its maximum height, and we can come along and say, you know what, let's call this our initial position now. And at that spot, we know that the velocity is equal to 0 meters per second. And now down here, again, halfway down on the way down, we'll call this our final position. So if we now look at our equation of motion, number 3 again, we'll write that out. So we have final velocity squared in the vertical direction equals initial velocity squared in the vertical direction, plus 2 times the acceleration times the displacement vertically. We know that our value for the location of the object will still be the same vertical position that we found before. That's halfway, right? And so we can write that down again as a final position of v squared over 4g. Don't forget that 4 in this case. And we can plug that in and now see what happens. All right, so I've canceled out the initial velocity here vertically because it's 0 meters per second. And now what we want to do is plug in for everything else, again, all in terms of variables. So let's do that. And we're reminded that we need to put a minus sign out in front because g inherently is a positive number, but the acceleration numerically is negative. And then we need to plug in for our displacement, final vertical position minus our initial vertical position. Now in this case, we got to remember, look, we're starting at an initial position here all the way at our max height. So no longer is that 0 right here. And then our final vertical position is halfway down. However, notice that is a positive number. It's still above our 0 position here down all the way at the ground. So we shouldn't put a negative sign here. That is a positive value for that. Now let's work that out and see what happens when we do the algebra. So we get negative 2g. Our final position is v squared over 4g. And our initial position was our max height of v squared over 2g, if you recall from before. Now, this is good because, look, we've got a negative sign out in front here, and you can't mathematically take the negative sign of you can't take the square root of a negative sign under the radical unless you have imaginary numbers, and we don't want to deal with any of that, and it would be wrong in this case anyways. So what we're going to then see is that the effect of taking 1/4 here minus 1/2, as you can see in the denominator, that's going to give us a negative 1/4 when we work out the algebra, which will make this 2 negatives cancel, and we'll get the square root of a positive number, which mathematically works out. So let's go ahead and do that. We get minus 2g, and this would now be negative v squared over 4g. And if really make sure you can work that algebra out. It's really not too challenging, but go from this step here down to this step and prove to yourself that it's definitely minus 1/4 when you do that. Okay, and if you do struggle with that, it's a little sign that your abstract reasoning skills probably could be strengthened by some good algebra practice that you might want to go back and redo to kind of get up to the level where that's kind of an automatic thing, which is helpful, especially when you're doing physics problems and there's a lot of variables like this. All right, so we can continue along and we can cancel out the g here, and we would cancel out the 2 and the 4, and we would be left with the following, which would be v squared all over 2. And that's going to equal our final velocity in the vertical direction. There's still a squared there. And let me rewrite the subscript here instead of v final y. Now we'll just write this as halfway down. Okay, cool. Now we got to take the square root. And again, we do that, and I'll write that right over here. So when we take the square root of this, we would get v over root 2. But I know what you're thinking. You're like, wait a minute. This object, this ball, is going down right here. So its velocity should be negative, and that's not coming out of our equation. And in fact, unfortunately, that's one of the limitations of this third equation of motion. It all has to do with the fact that it's squared here, and we have to take a square root. So in math class, when you do take the square root of a number, you get two solutions, positive and negative. So this is one of those little rare cases where you have to know that we got to manually put that negative sign out in front. Because again, this v here is our speed, which is always a positive number, but we are moving down in the negative direction, and so we'd have to put that minus sign out. That's one of the little tricky spots that you have to watch out for. And when you're doing physics, really always go into the velocity and double check, triple check that you got the sign of it right, or else it could cascade through your problem, and you don't want that. Now the next question that is really a great question, I can't stress this enough, is to think about which motion is going to take more time. To go from the bottom, where we're shot up at a speed v, up halfway, where we're now moving at a speed of v over root 2, or is it going to take more time to go from our maximum height, where we're not moving at all, back down to halfway, where we're now moving downwards with the speed of v over root 2 as well. So notice right here in the middle, we're moving with the exact same speed. It's interesting. We're moving, of course, up in one instance and down in the other. And the other thing that's similar about these two motions is the amount of distance that we've traveled here. So in the first case, we've traveled halfway up, which is represented by that line. And then secondly here, we've traveled halfway down, which is represented by this line. And those two lines representing that distance are exactly the same. So there's a couple ways to figure this out, and in fact we'll prove this using some equations where we actually get the amount of time in terms of symbols. But it's instructive to really be able to zero in on a concept, a real fundamental concept, and the concept is called average speed, or you could also use average velocity, but we'll just do average speed here. So if you really have a grasp of really what that means, what is average speed really mean, then the answer to this is pretty obvious when you just look at the values here. So go ahead, pause the video, and really think about that. Using the concept of average speed, which one of these motions is going to take more time for the ball to travel that distance? Go ahead. All right, so hopefully you thought about this. And if you look, I've written out the equation for average speed. It's very simple. You just take how far you traveled in distance, and then you divide that by the amount of time it took you to travel that distance. So if we rearrange this to then say the amount of time that you travel for is, well, whatever that distance is divided by that average speed quantity. Okay, now in both cases we travel the exact same amount of distance. So if we were to compare these two, this numerator value, the distance, would be the same in both cases. So all we really need to look at now to figure out which motion takes more time is to look at, well, which motion has the smallest average speed, because as this denominator here gets smaller and smaller and smaller, of course, keeping the distance the same, the time would have to increase. That's the way this math works out, right? So if we can identify which motion has the lowest average speed, then we have identified the motion that takes the longest amount of time, comparing these two. Again, because the distance of travel is the same in both cases. So which one has the smallest average speed? Well, let's take a look here at the first one. We're traveling at some speed v, and then we're traveling at v over root 2 up here at the top, right? So you can imagine, it's helpful to put numbers on this sometimes as well. So if we came in here and said, oh, okay, well, this is, maybe 30 meters per second, and maybe this would be 30 over root 2 meters per second. Get a sense of what that is, right? Great. And then we come over here and we look at it and we look, interesting. Well, in this second case right over here, we're not starting at 30 meters per second. We're starting at 0. So we're going from a speed of 0 up to a speed of, say, 30 over root 2 right over here as we get halfway down. That's interesting. And all of these values are going to have to go from 0 up to v over root 2, where here all of the values will go from v down to v over root 2. So we're always going to be moving faster during this motion here on the way up as compared to this motion right here. And then what will obviously end up happening is we'll cross over and our speeds will be exactly equal halfway up, which is kind of interesting. when we compare these two on the way up and on the way down situations, and then it would reverse. And as this ball then goes up to the top here, we would be getting slower and slower to 0, and as the ball comes down further and almost gets to the ground, we would be approaching our initial speed v here. All right, so then the answer, of course, is, well, the second motion here on the way down, that will have the smallest average speed here, and it will therefore then take more time for this ball to go from this position to that. And that's a really interesting result, because you might think that, well, hey, look, it's kind of like looking like the same motion. It's traveling halfway, right, either up or down. So maybe it would take the same amount of time, but nature's not working like that here. It's actually taking less time to go up halfway than it is to go down halfway like that. So a really cool result that comes right out of what we calculated in variables and the concept of average speed. Now our next question is, well, exactly how much time does it take to get halfway up to that spot? And to do that, here's the first equation of motion. And using some previous information that you now should have written down if you've been following along and writing this out, you can use this equation of motion to pretty easily actually find the amount of time it takes to do that. So go ahead and remember now, though, we need to change our initial and final positions to appropriate places for this particular question. So it says, how much time does it take to get halfway up? So we're going to again say now, all right, well, our initial position is right when we shoot this thing at speed v, and then halfway up, that will now be our final position. So pause the video, see if you can now work this out. You should have enough information in using this first equation to get it. Okay, so let's work it out here. And you should see that the velocity that we're moving at halfway up, which represents our final y velocity now, because that's our new final point, is our initial speed divided by the square root of 2, which we proved earlier. Now all we have to do is just plug that in, and we'll remember that our initial velocity was equal to positive speed v here. And so we'll plug that in and remember our minus g and do some algebra, and we pretty much have this worked out. So plug it in, and we get v over root 2, and do a mental check to make sure that it's positive, right? Well, v is always positive. That's our initial speed, and root 2, of course, is positive. So that works out. We're moving up, which is in the positive direction on the way up there. And then we have minus g times the amount of time that we've taken to travel halfway up. And I'm going to be very explicit and write the time to halfway up. And then add to that our initial velocity, which would be positive v here. Cool. So let's do a little bit of algebra and solve for this. We'll bring the negative gt on the other side, and then bring the v over root 2 on the other side. All right, so we'll get t times g equals v minus v over root 2. And now go ahead and work that out. I'll pause the video and just write it out quickly to save a little time, and you should get the result that has some square roots in it, and we'll try to make that look nice and pretty. So go ahead and try it and see if you get it. Okay, so here's the result at the bottom. The amount of time it's going to take to get halfway up is going to be equal to this ratio that we've seen before, the initial speed divided by the field strength g, multiplied by this interesting looking factor, 2 minus the square root of 2 divided by 2. Now, I tried to follow some mathematical, rules and principles, which typically says you don't want to leave a square root in the denominator. Oftentimes we abuse that in physics, but I'll be mathematically proper here and actually do that. And it's good practice, algebraically too. If you come up here and you just take a look at this expression, v minus v over root 2, how do we simplify that, right? So again, if you struggled with the algebra there, you might want to get some, practice in with that and making sure you can make that a little bit more automatic, because it definitely frees up some thinking power for the harder conceptual stuff in physics. But we'll come up here and see that we can factor out a v from each term. Then we would get 1 minus 1 over root 2. And now we can turn the 1 over here into just square root 2 over square root 2. And then now we have a common denominator here, and when you have that, you can then put it all under one division symbol here. So we'd get root 2 minus 1 over root 2. And now you can multiply anything by 1, and it's still 1. So let's multiply this whole expression times root 2 over root 2. And when you do that, the root 2 times the root 2 just gives you 2. And then the root 2 factored in here multiplied by that root 2 would give you 2. And then the root 2 here multiplied by 1 would give you a root 2. Lots of 2's here. And so you get v times 2 minus root 2 over 2. Okay. Now, that's we'll drill down into that in a little bit and actually do it out in decimal form because it's a little more helpful. This is a very kind of mathy way to show the result. But let's think about what it actually is telling us. And what I'd like you to do is go back into your notes or maybe back into a previous part of this video and find, or maybe you remember, how much time did it take to get to the top? Not halfway up, but how much time did it take to get to the top of the path? And compare that with what we just got. All right, so I've written both results here side by side, and I'll remind you the time to get all the way up to the top here was just our initial speed divided by the field strength. And we got that from exploiting the fact that the ball had a 0 velocity up here at the maximum height, or at the top, and we used the first equation of motion to get that pretty simply. Now look what's happened here. The time to get halfway up is the same v over g quantity, but now it's multiplied by some factor here out in front, and that factor better be less than 1, because if it was greater than 1, well, that would say it takes more time to get halfway up than it does to get all the way to the top. And physically, that obviously makes no sense at all. So this is a great moment to double check and see if the algebra that we just worked through and the physics we just did makes any physical sense. And if this number, this factor is greater than 1, then we know we must have made a mistake somewhere. Now, hopefully we didn't, and I know we didn't because when we work this out, we get v over g multiplied by a factor of 0.295. That's pretty cool. What that's telling us is the amount of time it's going to take to get halfway up is going to be 29% or 29.5% of the amount of time it's going to take to get all the way to the top. And that's pretty interesting. And you might stop to think about, I wonder why it's only 29 or about 30% of the time. And it probably doesn't take much thought to realize that, well, as we go from here to from the bottom up halfway up, we're moving pretty fast. We're moving our fastest actually up here, if we had a number 30 meters per second. But we're moving at speed v here, and then we're going to be slowing down. So on average, we're going to be moving a lot faster during this first half of the motion than we will be moving during the second half of the motion. And so it's going to take a lot longer of the total amount of time, v over g, to get up there. In fact, it's going to take about 70% of the amount of time just to go from halfway up all the way to the top. So you can really now, I hope, start to see that doing physics in this way, using these symbols and doing it all abstractly in variables, really starts to kind of open the can of such a simple physical phenomenon, just throwing a ball up in the air. And we can really start to see the amazing things that are happening and understand it in a totally different way, which is, again, like I've been saying, extremely powerful. One other thing to note as well here is making sure that the units are always working out whenever you're doing things symbolically like this. So just to do a little check on the units, we could come along and say, all right, well, what are the units of speed? Those are meters per second. Divide that by the units of the field strength of gravity, which are meters per second squared. And if you work this out, the meters cancel out. This squared cancels out with that seconds, and this guy comes upstairs, and we're left with units of seconds. So the next question we want to look at is, how much time does it take the ball to go up and then fall halfway down? So this problem can be worked out in a couple different ways. We'll look at one way of doing it, where we're going to start, again, right here at the initial spot when the ball is launched at speed v, and we'll try to figure out a formula that would tell us exactly how much time it takes to go from this spot all the way up and then come down to this final position where it's halfway down. Now, we know from before it takes an amount of time to get to the top of v over g. So now it should be very obvious to you that it's going to have to take more time than v over g in order to get down halfway, because we have to go up, which will take in a time v over g, and then we have to add on the amount of time it's going to take to come down halfway. So let's figure this out and solve it. And we can use, again, just the first equation of motion to figure this out because we have some information from the previous part of the problem. In fact, I'll remind you down here, something that we learned earlier in the problem is on the way down, when it's moving now down like this, we recall that it's moving with a velocity of negative v over the square root of 2. Right? And again, I'll just remind you that v is the initial speed here. And so we're moving down, which is what the negative sign is for, at a velocity of negative v over root 2. So use this piece of information with our first equation of motion, and now see if you can figure out the total time it takes to get from where we started initially to get to this spot on the way down. All right, so I've written out the equation, and let's make sure again that we get our signs right. You need to kind of double check this mentally. Our final velocity here on the way down must be a negative number. And there it is, negative v over root 2. Remembering, of course, that this v represents our speed and will always be a positive number. So we've taken in consideration the negative sign. And in fact, that is how fast we're going because we solved for that earlier in the problem. Then we also, again, have our negative g, t, like we've seen before, where this t represents the time it's going to take to go from where we started initially, shot up all the way up and then halfway down. And then again, our initial velocity at that moment of launch is v, which is our speed v, and we check our sign and we do have a positive velocity there, so that works. Now the rest of it is just algebra, so pause the video and see if you can work out that algebra and get it right. All right, so here's the result, and you can see that I've done the algebra, and we get this familiar expression 1 plus 1 over root 2, where we had 1 minus 1 over root 2 from the other part of the problem. And we can do the same algebra, and when you do that, you'll get down to this expression, 2 plus root 2 over 2. Now, what's interesting about this is when we work this factor out, it better be greater than 1, because it takes this amount of time, v over g, to get to the top of our path here. So it better take more time than v over g to get to the top and then halfway down. And sure enough, it does. If we go ahead and plug that into the calculator and work this out, you'd get v over g times, I believe, 1.705. So what that's saying is that it's going to take 1.7 about the amount of, a factor of 1.7, the time to get to the top, to get up to the top and down to halfway back down. Or in other words, 70% of the amount of time it takes to get up to the top would be required to get from the top back halfway down, which is an interesting result. So what we'll do next in this problem is add in a second cannonball and try to predict exactly the moment in time that these two cannonballs would cross at if they were shot at some particular time. So we'll ramp up the difficulty level even more here, and we'll have to rely upon the results that we've used to really see the conclusion to this problem. So here are our organized findings. We have shown that the maximum height will be the square of the initial speed divided by 2 times the field strength of gravity. We're going a speed of our initial speed divided by square root 2 on the way up, and we're traveling at that exact same speed, but on the way down, it's of course a negative velocity, so there's our negative sign. Remember that v represents our initial launch speed, and then the time to get to the top is just our initial speed divided by the field strength of gravity, and the time to get halfway up from when we launched it is, interestingly, just multiplied again by this factor out in front of v over g. It turns out to be about 0.295, and the time to go from when you were shot all the way up to halfway back down that we just saw is v over g multiplied by this factor. And I've kept it in the square root notation just to make it look nice, but it's also helpful to see what the decimal form is, and I've written that out too. So it's nice in the middle of a problem to kind of pause and just look at our findings here so we can remember what we've done. And now we really want to get to that harder question of the cannonballs colliding in midair. So let's see what that looks like. So the question is, at what clock reading should a second cannonball be launched such that it collides with the first at a position of half the maximum height? So if you look at the first cannonball, it gets shot up right at time equals 0. It goes all the way up and then comes back down halfway. And the amount of time to do that is given by this expression that we calculated. And then the other cannonball needs to be shot exactly at the right clock reading, and that's what we're trying to find here. But what it will do is it will start from the ground level and only get halfway up, and the amount of time to just go halfway up for that second cannonball will be given by this expression. But we want to know exactly at what time should we fire the second cannonball at after the first one has been shot so that they collide, right? It's not going to be this time here. That's just the time it's going to take for the second cannonball to get halfway up. We got to remember that this one has been moving as well previously in time, so we need to figure out how to do that. So I'll let you pause the video, and if you can just think about conceptually what's going on here, try to visualize the motion and think about time. And I've given some expressions for time here. You probably can work out the solution with just what's on this slide here. So take a minute, pause the video, and see if you can figure it out. So hopefully you figured it out, and what you should have found here is that all you really need to do is if you know that the second cannonball is going to take a certain amount of time to get to that halfway collision point up there, all you got to do is subtract that amount of time from how long it takes the first cannonball to get to where the collision point will be as well. And we have an expression for that already, so now we'll just go ahead and subtract those 2 times algebraically, and we'll get to our result. So I've gone ahead and worked it out here for you. You can see that the time, the exact clock reading that we want to launch number 2 at will just be the subtraction of these 2 times. And so here's our time for number 1 to go all the way up and come to halfway down. And let's subtract off of that the amount of time to go halfway up. And working out the algebra, you can see this minus sign over here is going to take this 2 and make it a negative, and this square root 2 make that a positive. And so we can clean up the algebra when we work this out, and you get to v over g times the square root of 2, which is just 1.4 times that familiar quantity v over g. Now what's interesting to notice here is that the time it took to get to the top of the path, the maximum height for that first cannonball, was just the initial speed divided by the field strength, or v over g. Now, the moment in time that we need to launch this second cannonball at is actually 1.4 multiplied by that amount of time to get to the top. So if you can just kind of like chunk in your brain that this quantity v over g is how much time it takes to get up to the top of that path, well, about 40% more of that time is when we need to launch the second cannonball at in order for this interesting collision to happen halfway up. So that's kind of interesting. It might be maybe different than you would expect in terms of what number would pop up here, but that would be the result. Now another interesting question here is, where will cannonball number 1 be located at the moment number 2 is launched? Now remember, the cannonballs are colliding halfway up. But right when that second cannonball is fired, of course it will be at ground level. But where will the first be? Well, it's not going to be at its maximum height, because if it was at its maximum height, the clock would read v over g when we needed to fire the second one. But we're not getting that. We're actually getting 1.4. So that cannonball, that second cannonball is actually going to, sorry, the first cannonball is actually going to be on its way back down, someplace on its way back down. We don't know quite yet where on its way back down, but it will be. So we're going to find that. So in order to do that, we now need to look at the second equation of motion. So I'm going to go ahead and have you again pause the video and see if you can figure out, using the second equation of motion, exactly where that first cannonball will be located at this particular clock reading now. Okay, see if you can work out that algebra. So I've written out the second equation here, and I've left some open parentheses to put in our information. So all we have to really know is, okay, where did that first cannonball start right when we launched it? It started at 0 meters. And what was its initial velocity at that moment in time when we launched it? And of course it was v, so we'll come and put that there. And then at what time are we now asking to know the final position? And the time we want to know the final position is at this quantity square root 2 v over g. So we'll put that in here. And then we'll also come and put that in over on the other side, not on the other side, but right here where we have to square the time. Made a slight mistake here. Let me make sure to put a g there. So v over g times root 2, we've got to square that. And then importantly, again, remember, this is a minus g because we've chosen down to be negative in this problem the whole time. So now we have a good expression. We can just work this out. And I'll let you pause the video and get to the result and see if you can get this exactly right. It's an important exercise, again, in your algebra skills. All right, so here's the result. Down at the bottom, we can see that it's this familiar v squared over g term that we've been seeing here. Remember, our maximum height was v squared over 2g. So this position looks like it is that same v squared over g, but then we have this different factor here, which is root 2 minus 1. And I've left it in the square root notation, or the square root notation here, just to make it look simple. But we'll convert that into a decimal form in just a second so we can get a little bit more intuition on it. And so the next thing that you should do here is pose the question, look, if this is where the object's going to be at the moment that we fire the second cannonball, this is where cannonball 1 will be located at the moment we fire the second cannonball. I wonder how high up is that? What percentage of the maximum height that our first cannonball will actually get to does this represent? Now, it's got to be greater than 50% of the maximum height because that's where the collision's actually going to take place. So whatever number we get for this next answer, it better be greater than a half or we've done something wrong. So think about that for a second. As a percentage, how high is this compared to the maximum height? So there's a simple way to do that, and again, we'll write out just so you can remember that the maximum height that our object travels to was v squared over 2g. All right, so if you wanted to figure out how much of a percentage this position is to our maximum position, what would you do? Well, you would divide. So you would divide these two expressions and then you'll get the result. So go ahead and work that out. Again, another important algebra exercise so you can really get used to using variables and doing a lot of algebraic manipulation to get to the final result. So pause the video, work it out, and we'll see if you got it. Okay, so here it is. We have our max height, v squared over 2g, and then we have the position that number 1 will be at when we launch number 2, which is what we just found, root 2 minus 1 times vg. And so we'll just divide these to find what percentage this height is of the maximum height. So when you do that, conveniently, look, the v squared over g terms, let's just cancel. And now we're just left with this expression, root 2 minus 1 over 1/2. And then we simplify that, and we work all that down into a decimal, and it looks like we get 0.82. So how do we interpret this? What does it actually mean? Well, what it means is that the position that number 1 is at, sorry, I forgot my number 1 right there. Let me put that in. The position that number 1 is at the launch of number 2 is at 82% of the maximum height. That's kind of cool. So if you could kind of draw that out, for example, we could imagine if we have the ground here, right? And then we come up, we say, okay, here's cannonball 1. It's going all the way up, all the way up. It's going to reach a maximum height. And then it's going to come back down and collide right there, halfway down. And again, please realize that there's not this little actual arc there. I'm just doing that so you can see it would go straight up and straight down in a singular line there. However, right here, we could then imagine this cannonball on its way down, and it's probably going to be somewhere, I don't know, right around here, traveling down. That's about 82% or about, right, of that maximum height. And right at that moment is when we would then want to fire this second cannonball right here, make that one going up. And if we did exactly that, then the physics we are learning here would have this collision happen right halfway. And that's pretty cool. I mean, you might think that you'd have to shoot this second cannonball maybe when this first one was at the maximum height. Sounds kind of logical, but actually that's not indeed what we need to do. We actually needed to fall a little bit, so it was here at 82% of that max height in order to have them hit halfway. So interesting result. Another piece of information that we should talk about as well is, will this cannonball number 1, when it is at 82% of the max height, is it actually moving up or is it moving down? We didn't really prove that one way or the other, but you can by thinking about, since the clock's going to read about 1.4 times v over g. And the time to get to the top was just v over g. Therefore, the ball must be moving down. And the velocity also must be negative in that case. Now, another interesting thought is we know that the velocity must be negative for Cannonball 1 on its way down at the moment number 2 is launched. We just proved that it's going to be going down. But I wonder how fast it's going to be going as a percentage of its original launch speed right at that moment. Not at the moment of collision, mind you. We already know what that speed's going to be. It's going to be v over root 2, and we found that before because it'll be located halfway. Now what we want to do is figure out when it's at 82% of its maximum height. And that's, again, the position this ball 1 is going to be at the exact moment we launch ball number 2. How fast is it going as a percentage of its original launch speed? So can you figure it out? How would you do that? What information would you need to know? Well, give you a little bit of a hint here. You have the clock reading. It's right here. It's the root 2 v over g. That's what the clock will read at the moment this ball is at that position, 82% of its maximum height. So again, pause the video and see if you can work out as a percentage exactly how fast it's going to be going. So you've worked it out, and using the first equation of motion, we can see by simply just plugging in for that clock reading here, root 2 v over g, and plugging in for our initial velocity, which is when the object was launched at with the speed of v, giving you a positive velocity there. And remembering again that gravity is down and negative in this case. We do the algebra there, and we come down to this interesting result where when you work through it, you get 1 minus root 2 multiplied by v. And thankfully, we got that negative sign coming right out of the math here, which means we did everything right. We have a negative velocity, and that percentage I was talking about is 59%. So when we're 82% of the way when we're 82% of that max height on our way back down, Cannonball number 1, it's going to be moving at a speed that's 59% of its launch speed as it travels down there. Now, finally, let's conclude. It's always important to do this, especially after we've gone through a lot of work in this problem. So what have we concluded? Well, to have two cannonballs collide at half the maximum height of the first, fire the second one up at a clock reading of 1.41 times the amount of time it takes the first to reach its max height. At this moment, ball number 2 will be moving up at speed v, while ball number 1 will be on its way down at 82% of the max height, moving at 59% the launch speed v. The collision will happen at 1.705 times the amount of time number 1 took to get to the top, and both will move at a speed of about 71% of their initial launch speed at that moment of collision. So this here would, represent a nice quality explanation of this problem, at least for the cannonball launch, for the two cannonballs, I should say. We would probably want to go into a lot more depth and explain in words what we did before, getting all of those different quantities like time to the top, and how we calculated how fast we're going, maybe halfway up, et cetera, et cetera. And then we could organize all of our findings again in a nice systematic way, showing all the variables and everything we got, and using subscripts to really label what the quantities we're talking about. And then that would represent a nice quality solution and a quality explanation for this entire problem. And there is a lot in this problem. We've done this very thoroughly, and we've also done it very generally, where we're not plugging in any numbers. In fact, this would work for any speed v, and it would work for any planet out there that has a constant field strength. Now that's quite remarkable that we've worked it out totally regardless of initial speed or any of that stuff. And that's part of the power of doing everything in variables like that, is you really get to see what the physics is, and you don't get bogged down by numbers. You get to the hearts of the relationships and how they're applied. Now, I do have one final question for us, a little bonus question. What if the gravitational field strength were suddenly doubled with a special gravity button that I would love to have but doesn't exist? By what factor would you need to change the initial speed by such that the cannonball would still reach the same maximum height as before the field strength was changed? It's an interesting question. Go back to that relationship about the maximum height and figure out, hey, what did that depend upon? And if we did double the field strength in terms of its magnitude, right? What would we have to do to the speed so we got the exact same maximum height? Really cool question. A good test of your understanding of proportional reasoning here. So pause the video and see if you can get that now. All right, so the solution here is, well, if you look, if we're going to take our field strength and go from a value of g to twice as much g, then we have to take our velocity or initial speed, I should say, and change that by a factor of only the square root of 2. And the reason is because when you, again, do proportional reasoning, you're plugging in the factors by which you're changing the values, and you're doing the mathematical operation that it says to do. So down here we can see it's the inverse relation. So we put 2g in our denominator, and then up here we put root 2v in our numerator, and we square that. And when we do that, we see these 2's cancel, and we're left with this original expression, v squared over 2g, which shows us that we get the same maximum height by doubling the field strength, but multiplying our speed by a factor of root 2. So again, both the numerator and denominator double, which ends up canceling out if this happens. So that's an interesting result as well. So let's say you fired something up at 10 meters per second. Well, now you'd be firing it up at about 14 meters per second or so if the field strength doubled, and that would have the ball going to the exact same height. It's kind of interesting to note that you wouldn't need to double the speed that you'd launched it at. Even though gravity has increased by double, we don't double the speed in this case. We do something different. That's kind of interesting. Now, that's something you would never want to memorize. It's not a useful piece of information really in general in physics. It's a unique result for this particular problem, and it's coming directly out of the equations. So these equations, these expressions that we're developing in variables here, they're telling a story about how nature will respond to changes. And it's a very powerful story that you now can hopefully understand and learn how to read. Now, I'll leave you with a few kind of things to reflect upon from this epic problem that we solved through. And if you've gone from the very beginning all the way to the very end and you've followed it now and you've understood it, well, then you've done a lot of great work at really taking you up to the next level in your abstract reasoning ability in physics here. But just think about how much we were able to learn here about nature just by throwing a ball up at some speed v. That's all we did, right? And you might wonder, what caused the results to be the way they were? Why did nature work this way? Well, the answer is that gravity, this weird phenomenon called gravity, close to the surface of the Earth of a planet, or close to the surface of a planet, changes an object's velocity at a constant rate. That is the key idea here that's causing all this to happen. That the rate at which we're updating our velocity is constant the entire time. And because of this, the equations of motion that we've developed predict all future positions and velocities. Of course, we ignore air resistance, which we're doing here. So what we have just done is we have worked out the consequences of all this motion and predicted the future, which is very amazing. And it's important to note that we don't want to try to memorize this specific result. It would be very futile to go back and take all of those little expressions that we just determined, and there was a bunch of them, like 8 or 9, if we wrote them all out, and commit those to memory. Not really going to help us. Instead, what we want to do is we want to practice the way of thinking and the process that we use to generate our results. That is the key. Every physical scenario out there is going to be different, and it's really futile to try to memorize all the different possibilities. Instead, physics is all about the process and the relationships between variables, and that's what we've done here. We've really gone through that process in great detail in order to get to these interesting results that we probably could not have predicted from the outset. So how do you get better at that process? Well, obviously, continued practice with challenging problems will develop and strengthen your ability to critically think. And what you'll find is that you're going to gain this amazing skill of facing a real tough problem where the path to the solution is initially unclear. It might be kind of clear which way to kind of start, but where the endpoint's going to be is not really going to be known at the start. However, through the process of thinking in physics, you'll find a clearing, and you'll generate some new knowledge like we did here. We generated a ton of new knowledge about the very simple process of a ball going up and coming back down, and the richness that it really exists in that one phenomenon. And ultimately, that process done over and over again through many different physical scenarios will, build up a new way of thinking, and you will totally see the world differently than before. And that's one of the really cool kind of life-changing powers of physics, is where you can now, look out at your world and see it in a totally new way, a way that kind of enriches your experience. So we've combined a great question with some, pretty basic math skills that you probably already have, some new information about the equations of motion, and applied that to a physical scenario we're all familiar with, and extracted out of that so much cool stuff that we can think about. And we learned a lot about the process of doing physics and the process of thinking through a physical scenario at the same time. And now we've reflected upon it in a nice way, and we're set up now to continue along on our journey and to solve some harder problems, some different situations that we've never seen before, and keep adding and building day after day. And when you do that for a good amount of time, especially if you're in a class taking a physics class over a year, if you just keep at that day after day, you'll build up this amazing strength at solving problems that you never thought you'd be able to solve. And so hopefully you'll be there with us and stay with this journey and continue to build our knowledge and see the world differently than we saw it before. All right, thanks.